This video is on section 3.3 notes, the theory of equations. If you are trying to do these notes before section 3.4, go back and do section 3.4 first. I think the book is in a little bit of a weird order for this, and it's a little bit easier to learn it if you do section 3.4 first. All right, so the n-root theorem tells you that if you have a polynomial of a degree n, then it has n roots. And it says to consider multiplicity, and we'll talk about that. So if you have something with a degree of 2, it means you should have 2 answers when you look for the x-intercepts or the roots or the zeros. When you have something with a degree of 5, you should have 5 answers or x-intercepts or zeros or roots. Degree of 3, 3 answers. Degree of 4, 4 answers. And the answers could be real or imaginary, so they're not necessarily something that's going to be able to graph. And when I graph this, I see 2 x-intercepts because we're going to consider multiplicity. But we'll talk about it so that when you actually go through and solve these, you'll be able to make sure, like, yes, I found all the answers I was supposed to find. Right, so this first one is a quadratic. This is a quadratic that we can factor, so that's what we're going to do here to find the roots or the x-intercepts. We're going to look for 2 numbers that multiply to 16 and add to -8, and the 2 numbers that do that are -4 and -4. So in the factored form, I would say that this is x minus 4 times x minus 4, or I would say x minus 4 squared. And so the real root is x equals 4, and it has a multiplicity of 2. And so this has 1 root, but that root happens twice. So there's 2 answers. The answers are x equals 4 and x equals 4. And so we expected 2 answers, we got 2 answers. All right. For the next one, I can factor this. It's a 5th degree polynomial. I have a GCF of 6 and a GCF of x to the 3rd. So I'm going to take out 6x to the 3rd and write the leftovers. 6 divided by 6 is just 1. X to the 5th, take out 3 of them, and we have x squared left over. 18 divided by 6 is 3. X to the 3rd I already took out. And so from here in the front, we have a root of 0, and that 0 has a multiplicity of 3. X equals 0, x equals 0, x equals 0. If I wrote this out, I could say this is 6 times x times x times x, and each of those x's are an x-intercept of 0. So that's 0 with a multiplicity of 3. That takes care of 3 answers. And then over here, I have x squared plus 3 is 0, and I can subtract the 3 over and square root both sides. And when I square root a radical, that was a double. Said the same thing twice. When I square root a negative, it turns into an I. So I've got I root 3 and negative I root 3. And both of these would be a multiplicity of 1. So 3, 4, 5, 5 answers. All right, for this one, if I was going to factor this, I would have to split this in half and factor by grouping. And unfortunately, this one does not factor by grouping. And so that means that I have to use the rational root theorem to be able to factor this one. So for the p-values, I've got 1, 2, 3, and 6. For the q-values, I have 1. And so that means that my possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So I'll plug in each of these until I find the one that gives me 0. So it's not 1. It's not -1. It's not 2. It's -2. So 1 times -2 is -2. Those add to -5. -5 times 2 is 10. Those add to 3. 3 times -2 is -6, and those add to 0. So if this is x to the third, that's x squared, x, and no x. So this is the quadratic that I'm solving. And if it was factorable, I would factor it. But there's nothing that multiplies to 3 and adds to -5. So that means this is a quadratic formula problem to find the remaining answers or the remaining roots. So I'm going to say -b plus or minus b squared minus 4 times a times c, all divided by 2a. So the discriminant is 13. And it looks like none of this can be simplified. I can't simplify the radical. There's nothing that can reduce. And so we have 3 roots here, and each of them have a multiplicity of 1. So the first root is -2. Then we have 5 plus root 13 over 2, and 5 minus root 13 over 2. And each of those is a multiplicity of 1. And those are the 3 answers. All right, for this one right here, x to the 4th, so I know I'm going to get 4 answers. I need to make sure, and if you look at this, you can see that some of these problems are written as polynomial functions, so it's like I'm looking for the x-intercepts. Some of these are polynomial equations, and I'm just solving them to find what the solutions are. And you'll notice that as I'm doing these problems, it doesn't adjust anything about how I'm solving the problems. If you wanted to be particular about it, you could say, well, if this is a polynomial function, then I really ought to write this x as an x-intercept and say 4, 0, and then write these as x-intercepts and say -2, 0, put this, 0, put that, 0, whereas these are just solutions, so I can just write them this way. But truly it doesn't matter. It just matters that we know that we can do this for functions, we can do this for equations. So the process is the same regardless. So here we have a polynomial equation again. I know it needs to equal 0 before I can do any solving. So I'm going to take that 3, add it to the other side. This problem you can't factor. The ones like this where they could have 4 terms and you could split it in half and factor by grouping, they're typically cubic problems, x to the 3rd. They don't have to be, but they often are. This one doesn't really look like that. It doesn't have a GCF, so this is definitely a rational root theorem problem. So P is 1 and 3. Q is just 1. So the possible roots are plus or minus 1, plus or minus 3. So negative 1 didn't, or positive 1 didn't work, but negative 1 did. So 1x to the fourth, 0x to the third, 0x to the second, 4x plus 3. So we have to make sure anytime there's a missing term, we put a 0 in its place. 1 times negative 1 is negative 1. Those add to negative 1. Negative 1 times negative 1 is positive 1. Those add to 1. 1 times negative 1 is negative 1. Those add to 3. 3 times negative 1 is negative 3, and those add to 0. So this is 1x to the third minus x squared plus x plus 3. This is what we're solving next. To factor this, if you could break it in half and factor by grouping, that would have been preferable, but it doesn't factor by grouping. If we take the GCF out here and look at the parentheses, and then there's no GCF here, take out a 1 here and look at the parentheses, they're not the same. So we have to do the rational root theorem again. So P is 1 and 3. Q is 1. The possible roots, again, are 1 plus or minus 1 plus or minus 3. The possible roots being the same this second time as the first time is kind of a coincidence. Sometimes they are the same, sometimes they're different. It just depends. So now I'm going to plug these into this equation this time. So negative 1. So we ended up getting that same root twice, which means we know that that root has a multiplicity of 2. So 1, negative 1, 1, 3. 1 times negative 1 is negative 1. Negative 2 times negative 1 is 2. 3 times negative 1 is negative 3. So this is, since that was x to the third, this is x squared minus 2x plus 3 equals 0. And so we have to solve this quadratic either by factoring or by the quadratic formula. I can factor this. Two numbers that multiply to 3 and add to negative 2. Oh, bummer. No, you can't factor that. So that's going to be a quadratic formula problem. I was really hoping there for a second. Okay, so quadratic formula, negative b plus or minus square root of b squared minus 4 times a times c divided by 2a. Negative 8. So the square root of 8 can be reduced. That's root 4 times root 2. So that's 2 root 2. And this has a negative with it. That means this has an I. So we have 2 plus or minus 2i root 2 over 2. That's so many 2's. Okay, so we can't touch the square root 2, but all these other 2's can be reduced. So 2 divided by 2 is 1, 2 divided by 2 is 1, 2 divided by 2 is 1. And so the imaginary answers, we don't even have to write it as a fraction anymore because we have 1 on the bottom. So I'm going to kind of ignore that. I have 1 plus or minus 1i root 2. So if I'm going to write down the solutions that I had for this polynomial equation, I would say I had -1 with a multiplicity of 2. I got that answer twice. And then I have 1 plus I root 2, 1 minus I root 2, and that adds up to the 4 answers that I expected. Okay. The reason that I'm doing so many of these problems is because I want to make sure that we can kind of be able to look at a problem and tell, how should I approach this? Is this something I can factor? If I can't factor it, I should be using the rational root theorem. And then in problems like the last one and this one, we're going to have to use it twice. I want you guys to not be intimidated. And so I know this is kind of tedious of the video to go over so many examples, but I do want to make sure that you understand what we're doing. So here's another problem with an x to the 4th. So this is a polynomial function that we would be graphing. So here we're kind of looking for x-intercepts. And so I'm just going to go ahead and use the rational root theorem here because I don't know how to factor something that has this many terms. So my possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Okay, so the first one worked, positive 1. And so I'm going to set up my long division. I know that the remainder is going to be 0. I just want to see what the next function is so that I can keep kind of bringing it down to keep factoring it. So 1 times 1 is 1. Those add to -3. -3 times 1 is -3. Those add to 4. 4 times 1 is 4. Those add to -12. -12 times 1 is -12, and that adds to 0. So this leaves me with x squared, nope, x cubed. Since that was an x to the 4th, this is x cubed minus 3x squared plus 4x minus 12. So P again so my possible roots are exactly the same as they were before. And like I said on the last problem, this won't always be the case. Sometimes after you've done that first step, this number ends up being different, and then you end up having different possible roots the second time. So all right, so I'm going to plug them into this next function. Maybe 1 will work again and it will be a multiplicity of 2. Nope. Okay, so 3 is the next root. 1, -3, 4, -12. So when I divide this, it's going to give me a quadratic equation that I can hopefully factor. That would be nice. 1 times 3 is 3. Those add up to 0. 0 times 3 is 0. Those add up to 4. 4 times 3 is 12. Those add up to 0. Okay, so this is x squared plus 0x plus 4 equals 0. And lucky for us, this is easy to solve. So subtract the 4 over, I get x squared equals -4. And then I'll square root both sides. X equals plus or minus. We're square rooting a negative, so we're going to have an I with our answer. And the square root of 4 is 2. So plus or minus 2i. So we do have 4 answers like we expected. 2 of them are real, 2 of them are imaginary. So the real roots are 1 and 3. The imaginary roots are positive 2i and negative 2i. All multiplicity 1. All right, for this last one, we have an x to the 5th. We have a polynomial equation we're going to solve with an x to the 5th. So this could be one where we have to use the rational root theorem multiple times. However, when I first look at the problem, I can see that there's a GCF of x. So I'm going to go ahead and take that out. And then you may or may not remember factoring problems like this, but this is actually factorable, and that's because this part right here is similar to factoring the quadratic x squared plus 3x plus 2. It's just that these terms have been squared. So we're going to look at how we would have factored this. 2 numbers that multiply to 2 and add to 3. And the factors for this would be 2 and 1. So if we were factoring this, we would have said, oh, it's just x plus 2 and x plus 1. But we weren't factoring a quadratic. We were factoring something that was x to the 4th. And so it's actually this squared and this squared, which means that our parentheses are actually x squared plus 2 and x squared plus 1. So if we were to put it in the factored form, it would look like this, the x from the beginning. X squared plus 2, x squared plus 1. Thankfully, those are pretty easy to solve. This x is just 0. Here we have x squared plus 2 equals 0. So x squared equals -2. And then we can square root both sides. And so x is plus or minus, and then we have an I root 2. Similarly, for x squared plus 1, it also equals 0, and then we end up with x squared equals -1, and then we can square root both sides. This is going to be an I as well, but then the square root of 1 is just 1, so it's just the square root of I. So we do have 5 answers. All of them are multiplicity of 1. We have 0. We have positive I root 2 and negative I root 2, positive I and negative I. So there's our 5 answers right there. All right. For the next part of the notes, we're going to go backwards. So we're going to take the roots that we have and we're going to write equations from them. So before we really get into that, I want you guys to recall that when we find imaginary roots and irrational roots meaning roots that have radicals in them, those roots always occur in pairs. So this is a radical, it's imaginary and radical, but plus or minus. Here it's imaginary plus or minus. Up here, imaginary, it's got a plus or a minus. Let's look at some other ones. This one right here has a radical. We got a plus or minus in there. Where else? This one, imaginary and a radical, we got a plus or minus. So they always have a plus or minus. They always come in pairs. And that's because those roots typically come from the quadratic formula. Sometimes you're just square rooting something, but they typically come from the quadratic formula. So if you were solving this problem, for instance, you would plug all the numbers into the quadratic formula, and then at the very end, you would have 1 plus or minus 2i. You always have two answers. So this imaginary roots occur in pairs, the positive version, the negative version. So this is called the conjugate pair theorem, is that if they give you one of the roots, they say, oh, one of the roots is 1 plus 2i, then you can automatically say, oh, the other one has to be 1 minus 2i, because they always come in pairs, right? So let's go ahead and use that idea to try to write some polynomial equations. So here's the first one. We're just going to make sure that we remember how to look at a graph and be able to tell how to write the equation out. So here, if we have a root of positive 2, when we write it inside the factor or inside the parentheses, we would write x minus 2. It always changes the sign, so this would be x minus 4. So if I wanted to write a polynomial equation for this, I would say y equals x minus 2 and x minus 4. And if they said that the factored form was okay, or that the linear factorizations were okay, then I would leave it like this. But sometimes they want the standard form. So I'm going to go ahead and FOIL this out, multiply this out so we can see the standard form. So we have y equals x squared minus 4x minus 2x plus 8. So y equals x squared minus 6x plus 8. And you can call this a quadratic. That's very specifically what that function is. Or you could say it's a polynomial. A quadratic is a type of polynomial. All right. Here are some other roots from another polynomial. They said that they have a real root of 2 and then an imaginary root of 1 minus I. Well, we know from the conjugate pairs theorem that these imaginary roots have to come in pairs. They come from the quadratic formula. So if I have 1 minus I, I also have 1 plus I. Right? And then we know from previous experience that when you have your roots and you put them in parentheses, you always change the sign. So for the first root, I'm going to say x minus 2. And then for these, I'm going to be very careful to change each sign as I write it in parentheses. For the first one, I'm going to say x minus 1 plus I, x minus 1 plus I. And for the second, I'm going to say x minus 1 minus I, x minus 1 minus I. And then when I multiply this out, the i's get a little bit messy unless you multiply them together. So I'm going to multiply these two sets of parentheses by each other. And then once I'm done with that, then I'll take that product and I'll multiply it by x minus 2. Now, some people are comfortable foiling 3 terms times 3 terms, but I don't love it. And I have found that when students do it, sometimes they make mistakes. And so whenever I have something to multiply that's more than just 2 terms times 2 terms, a binomial times a binomial, if I have something like this, which is a trinomial times a trinomial, I always use a box. So I'm going to do it this way. You don't have to do it this way. If you prefer to kind of FOIL it out, you can do that. So I'm going to write one of these along one side of the box and another one along the other side. X minus 1 positive I, x minus 1 negative I. And then I can just multiply them together like a multiplication chart, basically. So x times x is x squared. X times negative 1 is negative x. X times negative I is negative ix. And don't worry about that, it's going to cancel out. Negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. No, I don't know why I wrote the positive. Just positive 1. Negative 1 times negative I is positive 1i. I times x is ix. Negative 1 times I is negative 1i. And then I times negative I is negative I squared. All right. Now, the positive ix and the negative ix cancel. The negative 1i and the positive 1i cancel. And then I have to remember what I squared means. And there's actually an I button on your calculator way down here. So I squared is negative 1. You can type it in your calculator or you can just remember it. I squared is negative 1. So this is the negative version of negative 1. This is positive 1. Okay, so the inside of this became, I have x minus 2 still. The inside of this became x squared minus 2x plus 1. Okay, so now I need to multiply those out. So I'm going to do a box again. I'm going to have a box with 2 multiplied by 3. 2 terms multiplied by 3 terms. X times x squared is x to the third. X times negative 2x, negative 2x squared. X times 1 is x. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 2x is positive 4x. Negative 2 times 1 is negative 2. Okay. So y equals x to the third, negative 2x squared and negative 2x squared, negative 4x squared. 4x and x is 5x, and then negative 2. There's our polynomial. And if you want, you can even graph it and make sure it has one x-intercept of 2 and no other x-intercepts. All right, next we have negative 6 and 3i root 2. If I have a positive 3i root 2, then I should have a negative 3i root 2. Okay, so in my parentheses, I should have x plus 6, x minus 3i root 2, x plus 3i root 2. And I'm just going to start by multiplying these together. I don't feel like I need to use a box. I have 2 terms times 2 terms, and those are pretty easy for me to work with. So I'm just going to FOIL these. X times x is x squared. X times positive 3i root 2. So that's 3i root 2x, which is ugly, but don't worry, it will disappear. Then I have negative 3i root 2 times x. And then I have negative 3i root 2 times positive 3i root 2. Okay, so positive 3i root 2x, negative 3i root 2x, those disappear. Negative 3 times 3 is negative 9. I times I is I squared. Root 2 times root 2 is root 4, which is just 2 times 2. These are all multiplied together. So I've got negative 9. I know I squared is negative 1. Negative 9 times negative 1 times 2 is positive 18. So that's just x squared plus 18. And then I can kind of drop this down. And I can FOIL these again because I still just have 2 terms times 2 terms. X to the third, 18x, 6x squared, something bigger than I know, 108. So the polynomial function is x to the third plus 6x squared plus 18x plus 108. And if you wanted to double check it, you could graph it in your calculator and make sure that it has an x-intercept at -6.